Hello students. Today we are going to discuss about purification and separation. In this particular module, what we are trying to look at it is what kind of toolkit mixtures would have in order to separate their individual components. And that's primarily we would be focusing and discussing in this lecture and the lectures to follow. In this particular module, I would take up chromatography as the fundamental science behind this separation technique. And as we would progress in the following lectures, I will take you to a fascinating journey of chromatography and how it has evolved into gas chromatography and HPLC and certain new things which have come up in these separation methodologies. So, in this lecture plan, we would be addressing a few questions regarding separation techniques, and I would like to give you a very introductory commentary on separation methodologies, separation science. The first question that should come across as far this separation methodology is concerned is why there is a need for separation methodologies. Addressing it, I would like to take you to the age-old practices which have been prevalent in separation methodologies, and since after going across those age-old methods, we would take up scientific adaptations, how science has taken up those methods into its core and what has come out. And then lastly and most importantly, I will apprise you about chromatography, a separation science which has taken this whole separation paradigm by a big leap. So, to begin with, the first question, why do we need separation? I will try to relate it with something very fundamental, something which most of us would know. Probably, all of us might be aware that when petroleum is taken out as crude, it is of no value. It is worthless because it is a mixture of several components which in that crude mixture has no value. What happens later on is a process or a chain of processes which converts this petroleum as a wasteful product into something highly useful. How this is being done? That is where this science of separation comes into picture. What converts into this not useful compound into something like a gold mine is nothing but separation science. What it basically does is, as you could see here, we take this crude product in and apply heat to it, a process which is known as fractional distillation, and then using this process what we find is that this crude useless product is separated into its various constituents. Each of that constituent has wonderful and extensive applications for mankind use, and all of us know that. This is not one inclusive example why we need separation science. Separation science is used in all the variety of applications that we come across. We take medicines and each of that medicines, each of that component is a single compound, being isolated from, let us say, tens and fifteens of constituents, and that is where separation science comes handy. So, the examples are endless, and that should bring home a point as to why we require separation science. Separation science and this technique has evolved and was in practice since ages, maybe till when the man acquired ways to use the tools and for its benefit, maybe from that time. We will start to follow this, look at certain examples which had some use even in our day-to-day lives. Examples like filtration, example like sedimentation, decantation, dissolving and separating some constituent, sieving, evaporating, and then their scientific adaptation of all these methods into some more refined ways to identify and purify the components. Techniques like crystallization, like flotation, distillation, centrifuging, and last but not the least, chromatography. And that's where we are going to focus the rest of the lectures on. But for today's lecture, I wish that we take this journey backwards and we look to all these primitive and their scientific adaptations, as I call, and look them with some perspective. So, we begin with the filtration. Who has not seen it in childhood? And that might have been one of the famous, the most interesting chemistry which a child does all by himself. You dissolve sand in water, you take a filter paper and a funnel, and then start pouring that mixture through that funnel. And bingo, for a child it is nothing less than a miracle. The sand will stay on top and what you get is a crystal clear water. That is the beginning, that is the journey through which we start to understand and appreciate and befriend this science of separation. This is another example, sedimentation. This is something again many of us might have come across, and this is the science which not only humans, this is a science which nature practices. What basically sedimentation is, you have certain particles which will stay in a solvent or water mostly, and then gradually as the time progresses you would note that those particles will slowly sediment and will get separated from that particular mixture. Now, I told you that this is a science which nature practices. How does nature do that? Just look at it. This is an image of a delta created by a river. How has this delta been created? There is a vegetation which you could probably see. River when flows through, it carries a lot of particles, a lot of mud and other gravel and lot of things, which then during the course gets sedimented. And once they sedimented, they start to form this landmass close to this delta. That's a process nature adopts. Taking this forward to another process of decantation. Decantation is just a modified sedimentation where you take sedimentation one step forward. What we do, something which is sedimented can be separated by taking the supernatant out, which is being done here. So, this is decantation. Another method which has been widely practiced in separation science since ages is flotation. And flotation is just opposite of sedimentation. In sedimentation, what we saw is that the particle, the solute which has to be separated will settle down. In flotation, those particles would not settle down, they would rather come up, they would rather rise up to the surface. And once they rise up to the surface, you can just take them up as broth and then it can be separated. This science of flotation is primarily used in mineral sciences, wherein this example as described, there is a mineral, what we do, this ore is being treated in the beginning and those air bubbles come in, and that ore particle is treated ore particle would then come up as a float and that float will be separated. So, that is a method of purification. Another example is like oil would float on water and that can be separated by using flotation. Another very common example is an example of sieving, and I would be surprised if any of you might not have seen it in your daily lives. If not, you must have seen, especially in the villages, women sieving wheat or sieving rice through those big sieves. So, it is a basic, it's a method in which there is a differentiation between particles based upon their size. You use a sieve and sieve will let some size of particles pass through and it would prevent the others to stay on top. An age old practice. So, the point I am trying to bring home is this science of separation is something, it is prevalent everywhere. This is another example of dissolving an impure mixture, and example that I picked up is a mixture of sand and sugar. The easiest way to separate it is you dissolve it in water. So, sand will not be dissolved, whereas sugar will. So, what we do? We just filter it out. So, what we get is sand separated from sugar. All of this, I believe, has come out from just a commonsensical approach wherein we have behaved as scientists, all of us. Evaporation is another science. Evaporation, another scientific, another methodology for separation, and examples are abundant. One example we come across is just taking out salt from seawater. So, the solvent is evaporated and the solute remains behind. Now, these are all, whatever we discussed so far, were more commonplace examples underlying the importance of this important phenomena of separation. Now, how science has evolved and taken them up into its scientific practices is what we are going to see now. As an example, the first one I am going to take up is crystallization, a very important process for separation. What we do in crystallization? So, let us say you have a mixture containing a solvent having more than one solute, and we need to take one solute out of that mixture. What we do? We heat the mixture, and then once we heat the mixture, one of the solutes almost reach its saturation point. Now, if you cool it down, that solute, if it has a propensity to get crystallized, would just form excellent crystals and get purified and separated in highly pure form. Now, for this to happen, one needs to have a solute which has this propensity or likingness towards getting crystallized. Can we see it in a normal day-to-day life, or can we have a commonplace example? Well, I guess we can have, and this is one example where you could see for yourself this process of crystallization. Add some sugar into a hot water, and then once you add this, dip a thread or a wire to this hot solution and let the solution stand for some time, let it get cooled by its own. After some time, you would start noticing that the wire which is inside the water would have some excellent fine crystalline growths around it. Those crystals are nothing but crystals of sugar. So, to begin with, that water might contain other impurities, but then it is sugar which has crystallized out and has got purified. So, that is what I meant when I said you got to have a solute which has a propensity to get crystallized. Another scientific adaptation, as I would call, is this process of centrifuging, and it is scientific adaptation of sedimentation, the process we saw in the previous slides. Now, as I told you in the previous slide about sedimentation, the real force underlying this process of sedimentation was the force of gravity, wasn't it? Now, the limitation with this force of gravity is it would take immensely long time for a compound, for a component to get settled down. We do not have that much of time, right? So, what we do? we try to reinforce this gravitational force with another force which we call is centrifugal force. And that centrifugal force comes in handy once you rotate a mixture, rotate a substance at very high speed. So then the higher molecular weight components, they tend to sediment using this centrifugal force, which by the way is of the order of, let us say, 100 to 500 times more than gravitational force. Okay. Where do we find applications of this? We find applications of this onto the blood tests. All of us might have gone one time in a pathological laboratory and got our blood tested. What happens there? The pathologist wants to count RBCs, right? So, for that he needs to separate your blood sample into RBCs and other cells and plasma, which is devoid of all those cells. So, the cells are those high molecular weight components. What he would do? He would put that blood sample through this machine called centrifuge, and then after some rotations, this is what you get. The plasma and blood cells would be separated. Distillation, another very interesting methodology, is quite routinely used in scientific laboratory, and tell you what, it is again a scientific adaptation of something we just saw, and that process was evaporation. So, in distillation, what we do in a more scientific way, we take out a mixture containing a solute and a solvent, and remember, now the condition for a solute to get separated is it should be volatile. It should have a boiling point which falls in range when you heat the compound. So, once you heat the compound, first of all, there is some scientific mistake in this picture, since it shows a direct heating. You never heat a flask directly. There should be something, there should be ideally a water bath, and I believe that this is what you would practice once you enter laboratory. Do not heat a compound directly. So, let us say the volatile components will, upon heating, will go up, and they would then enter what is called a condenser, which is the cooling unit. Okay. So, it gets condensed and you could collect it here in the collecting chamber. So, this is how you would separate a volatile component, let us say, from a non-volatile one, or let us say a mixture of non-volatile or a volatile components having hugely different boiling points, and that can also be separated. The example I showed you in the beginning of fractional distillation of petroleum products was also an example of more refined distillation, in which many components were volatile, but they still were able to be isolated on the basis of changes or difference in their boiling points. This is just another example of a distillation process, salty water to distillation, and it is the salt would be kept back once you heat this water off, and water would be collected here. This brings me to the last but not the least method of chromatography, and this is a separation science which is most recent out of all the methods we have discussed. If I have to draw an analogy, I would rather draw an analogy with, let us say, what we had been seeing so far was like using different methods and different types of lamps, right, to lit up a house, and then chromatography comes in as a bulb. So, you know what kind of quantum jump as far as its innovation, the level of innovation is concerned in this separation science. Where is the need for this separation science? Why I am saying it is a quantum jump? That can be easily visualized. Let me give you an example. Let us say I have a mixture of not 2 components, not 10 components, let us say I have a mixture of 100 components, and I need to see, or you need to see, each one of those components, or let us say one out of those 100 components as a pure compound. Let us say it is that pure compound which is a drug molecule. Can you use distillation? No, it is very difficult. Can you use all the methods like filtrations, centrifuge? No, nothing will work. So, there is a strong problem, there is a problem in hand, and that is precisely what was happening in the early 20th century. When the science was on a rise, there were biologists all around, there were chemists all around, they were making molecules, they were deciphering what is inside a cell, what type of enzymes are there, what type of components are there, and there was still no proof of concept. They could not isolate a single compound out of that. And certainly it was it was felt that there is a great need of a science which can purify those components in one shot. That is what is most specific about chromatography. You can take n number of components and in just one shot you can isolate all those components. Okay. So, how this has evolved, and this is probably the last point I am going to discuss in this lecture. It has evolved from something very fundamental, and that fundamental is what we know is partitioning science, science of partitioning. What is that? I will give you an example. Now, let us believe there is a solute X, and this solute X is dissolved in a solvent A, right. Now, this solvent A, apart from having this solute X, also contains many other solutes, and you want to take this X out. There is a methodology which we have not discussed in this. You can probably bring in a solvent B, provided that the B solvent has philicity or likingness towards this X more than the philicity of A towards this X. So, you add this solvent B to solvent A containing X. You shake it up, you let it settle down. There is a precondition that this A and B should not react. A and B solvents should be immiscible. So, you would generate two different layers. After settling them down, what happens? This X, which was previously completely dissolved in A, now has partitioned itself into B and A. So, it has become more in B and less in A, right. You take this B out, add some fresh B and repeat the process, and repeat it, let us say 3 or 4 times. What do you observe after 4 or 5th time? After 5th time, you would realize that you have taken all the X out of A selectively and have transferred it into B. This is the science of partitioning, and that is a concept and is a basis for chromatography. We take two solvents like in partition chromatography, but those two solvents, instead of those two solvents, we call them, there are two phases. There is a stationary phase in a chromatography which can be liquid and it also can be a solid, and then there is the second liquid which we call is a mobile phase, and the objective remains the same. You have to take that X out. So, X will need to either partition or adsorb within those two phases and would get out. We would read and learn more about this methodology in the following lectures. For now, let me finish by saying that this science of chromatography is the start of a new journey, a new leap, and I am very sure that once we would start into those nitty-gritties of this science of chromatography, you would enjoy, and at the same time you would be astonished at the depth of this subject. Thank you very much.